This is a video where we are going to learn about how to frame the partial differential equations. Till now in the last lecture we have learned about what the partial differential equations are and how we can say that the given partial differential is of which order and degree, and we have learned about that a partial differential equation can be linear, non-linear, and if it is not linear it is possible that we can have a category as semi-linear or quasi-linear also. Today we are going to explore about formation of the partial differential equations. So let's start that if we talk about a partial differential equation to be created, so there are two ways from the given relation. First is by eliminating the arbitrary constants, and the second is by finding relations between the derivatives. This is the first rule, that if we have an equation to be calculated for the relation, here we have function of x, y, z, a, b that involves the variables as x, y, z, and here a, b are arbitrary constant. Then for this given relation I am expecting to partial derivation relation of f in x, y, z and a, b. I want to create a partial differential equation. First, so I have to differentiate partially with respect to the independent variables x and y, and finally we have to eliminate the constants appearing in this relation. Once the equation is free from a and b the constant, it will be the required partial differential equation. Now the next thing is, can we think about that when I am creating a partial differential equation, will it be unique, or the number of partial differential equation could vary, or it can be obtained in a different forms? Here is the answer, that there are three situations in which we can say there is a unique PDE or there could be more than one PDE. So this is the first situation, that if the number of arbitrary constants, here we have taken a and b, if the number of arbitrary constants is less than the number of independent variables, then it can give rise to more than one partial differential equation of order 1. Okay, the emphasis on partial differential equation of order 1. So we are saying that if the number of constants is less, means might be possible I am having only a, there is no b, right? So we are going to eliminate only this a. So it could be different ways that you and me are doing. So it could lead to more than one partial differential equation of order 1. Here we have an example. We are saying z is equal to ax plus y. So I can see that here we have only one constant. So let us try to eliminate it. So if I need to differentiate with respect to x, on differentiating with respect to x, I will get del z by del x is equal to a, right? So it means I got the constant. So if I substitute it back, it will leads to z is equal to x into del z by del x plus y. This is a partial differential equation we have obtained, right? But if I differentiate with respect to y, what I will get is, I will get 1. So it means I can write it down as del z by del y, that we have learned can be written as q is equal to 1. So is it a partial differential equation? Obviously yes. So we have obtained two partial differential equations from a relation that involve only one constant, which is less than the number of independent variables x and y, right? So here we have the second situation, when the number of arbitrary constants is equal to, this time we are saying they are equal to the number of independent variables, means we have two constants a and b and two independent variables x and y. Then we are saying it will give rise to a unique partial differential equation of order 1. Means this time if I will eliminate the constants a and b by differentiating with respect to x and y, then it will lead to a partial differential equation of order 1 and it will be unique. So let's do for this example. If I differentiate this with respect to x, so what I will get is a into del z by del x is equal to a square, right? X will give me 1, so a will cancel out and I will get del z by del x is a, means the value of a is del z by del x, right? I got the value of a. Now differentiating with respect to y, differentiating with respect to y, I will get a into del z by del y is equal to 1, or I can say a into del z by del y is 1. So this is, I can say q is equal to 1 by a, and from here I will get p is equal to a. So what we are getting, I have not eliminated b by these equations, but whatever the relations are appearing, I can say from here I can conclude that P into Q is 1, and this is nothing but the partial differential equation. Right? Now let's start for the third situation. Here we have the third situation when the number of arbitrary constant is greater than the number of independent variables. It means right now you can see the example. Here we have the relation involving three constants A, B and C. So what it leads to, if I will eliminate the number of arbitrary constants appearing here, it will lead to a partial differential equation which is of order greater than 1. So let's try. This is what we have the equation as. Now if I differentiate it with respect to x, it will give me A, x will give me 1, and from here x is 1 plus cy. If I will differentiate with respect to y, it will give me b plus cx. So I got these two, but it is not leading to any answer. So what I can do, I can see that here if I will differentiate it again, I will get del 2z by del x square, and it will leads to 0. If I differentiate with respect to y this again, then it will also give me 0. So what these are actually the partial differential equations we are getting, and it results in r is equal to 0 from the first one, del 2z by del x square is 0, and t is equal to 0 as we are getting del 2z by del y square is 0. Right? Now what else we can do? If I simplify these two, now how? Let us try that I will differentiate the first one with respect to y. So I will say del 2z by del x del y is equal to, a will give me 0 and it is c. Right? And if I differentiate the second one with respect to x, so del x del y is equal to c. It means it is for sure that we are getting c as s. From both we are getting the same. Now when c is obtained in s, the first equation, this one, let me number it as 1 and this one 2. So from first, if I write it down, I can say a is nothing but p minus cy, and c is s into y, and from 2 we are getting b. b is equal to del z by del y is q minus of c, that is s into x. Now if I substitute the value of a, b and c in the main equation, let me write down here z is equal to a into x. I have substituted p minus sy as a, b is q minus sx into y plus c is my s, xy. Now if I simplify it, it will be px minus syx, qy minus sxy, and plus sxy. Now if I simplify it, what will leads to? It will give me px plus qy minus of sxy, and this is what we got as z. So what we can observe is that we are getting this, let me name it as third, this is the fourth one, and this is the fifth one. So the third, fourth and fifth are leading to the partial differential equation. So this is how the three situations may arise, and we can say a partial differential equation may be unique only when the number of constants and number of independent variables are equal, and otherwise it could be more than one. Here we have an example. We need to find a partial differential equation by eliminating a and b from this equation. So let's try. If I differentiate with respect to x, I will get del z by del x is equal to, from here x will give me 1, so it is equal to a. If I differentiate the equation with respect to y, it will give me del z by del y is equal to b. This y will give me 1, and otherwise all are 0. So if I got the value of a and b, let us say this is number first and number 2, and let me mark this one as asterisk. Right? So I can say putting values of a and b from 1 and 2 in asterisk. What I will get is, I will get z is equal to a is del z by del x in PQR form. So it's easy to depict that I can say z is equal to, so this is the resultant partial differential equation. Let's start with another example. Z is, let me mark it as asterisk. So I can say differentiating asterisk with respect to x. If I differentiate with respect to x, I will get del z by del x is equal to a, and x will give me 1. And if I differentiate asterisk with respect to y, what I will get is del z by del y is equal to, now again y will give me 1 and it gives me a. So I can say from first and second. Now this time I can see I am not able to get b, but what is the relation from first and second? From first and second I can say del z by del x is nothing but equal to del z by del y, or I can write it down as p is equal to q, which is the required partial differential equation. Let's start with the third one. Again for practice, let's do it. So here we have, let's mark this as star. I can start with the same procedure, differentiating star with respect to x. I will get del z by del x is equal to a. X will give me 1. This is the first equation we obtained. Then differentiating with respect to y, what I will get is del z by del y is equal to, now this will give me a square as such, and y will give me 2y into a square, and b is 0. Again we are not getting into the picture the constant b. So what I can observe is, again if I write down from first and second, I can say a is equal to p, and here if I substitute the value of, so I will get q is equal to 2y into p square, right? So this is nothing but the partial differential equation, right? Now there is another rule that we have discussed, that till now we have done when I am getting the equation and we have eliminated the constant by differentiating with respect to x and y. Now the other type of equations could exist when we are getting the functions. So we need to eliminate those functions differentiating with respect to x and y. Let's try some examples. We have the first example, and you can see instead of getting the whole relation, I am getting x plus y plus z is a function of x square plus y square plus z square. How I will be getting the PDE? By eliminating this. I will differentiate asterisk with respect to x. If I differentiate with respect to x, I will get 1 for x, y will give me 0 plus del z by del x is equal to, now here I have a function of x square plus y square plus z square, and if I differentiate it, what I will get is, I will get its derivative. It's a derivative of this whole function, and then we are differentiating with respect to x. So x square will give me 2x, z square will give me 2z and del z by del x. Let me mark it as first. Now again differentiating star with respect to y, what I will get is y. Now again the same thing from first and second. If I simplify, let me write on in the short form 1 plus p. Let me divide the two sides so that this function will cancel out. So 1 plus p by 1 plus q will leads to, I can take 2 common, and it will give me 2x plus zp divided by 2x y plus zq, and if I rewrite it, it will give me 1 plus p into y plus zq is equal to x plus zp into 1 plus q. So you can leave it right now here, or you can simplify it to get the PDE. But I am leaving it here. I think it's fine. We have eliminated the constant f. So here we can see the answer. It's the same. One in the form I am getting, and another is the simplified form. Both are right. Let's start with another example. Here we are getting z is a function of x square plus y square. So be sure to pause the video and try it by yourself. I think you can do it. So again the procedure is differentiating with respect to x. So if I differentiate with respect to x, del z by del x is equal to a function of x square plus y square into twice of x, and if I differentiate with respect to y, I will get del z by del y is equal to function derivative into, now this time with respect to y, so I will get 2y. So this is my first, this is my second. Again if I simplify it, then from first and second I can say p by q is equal to 2x by 2y, or I can simplify it, then py minus qx is 0. So this is the required partial differential equation. So let's summarize what we have learned. We have learned about a differential equation till now, what is ODE and PDE. We have learned about finding out the order and degree of a partial differential equation, its classification, and then after we have learned about formation. Right? So this is being covered in the last and this lecture. Now what next we are going to learn is, we are going to start with linear partial differential of order 1, and we are going to study about the Lagrange's method to solve it. Thank you. Have a nice day.